Okay, welcome again, everybody. I think with you all looking at the title of this section, you're all probably pretty excited. So I think you've heard, at the very least, anecdotal remarks about the Fourier series, and today is finally that day where we're going to investigate it and see all of the beautiful properties it has. There are actually I can think of 5 different ways to come up with a derivation of the Fourier series, and we are going to develop ours from the context of complex analysis, just because that previous section talking about the vector space of analytic functions bleeds into this so perfectly. That we're going to start by just considering the analytic function centered at 0, and I've given these a subscript of a 1. And by the subscript of a 1, I mean that you'll recall this is the way you can calculate the radius of convergence of some analytic function. And I'm claiming that the radius of convergence of all of these in here is greater than or equal to 1. Now it turns out this is also going to be a vector space. So it's a smaller vector space. This is a strict subset of the vector space. Analytic functions centered at 0. Because the analytic function centered at 0, we don't require anything about the radius of convergence there. But this vector space is smaller. We're requiring that all of these radii of convergence are strictly greater than 1. And what we're going to do is look at specifically this collection of complex inputs. So I'm going to jump over to the whiteboard so we understand what this collection of complex inputs is a little bit more broadly, because I didn't cover it super well strictly in the complex analysis section of the book. So here we are at the whiteboard, and let's investigate the complex numbers with magnitude equal to 1. Now, it shouldn't be a surprise that if we represent these on the real and imaginary, if we represent these on the complex plane, then this is the unit circle. And so I'll plot that on here just as a nice big circle. So this is at 1, this is at I, and this is at -1, this is at -I. And these are the complex numbers of distance 1 away from the origin, right? A circle is exactly the points of distance 1 from the origin. Now, if we think about the unit circle in a trigonometric sense, trigonometrically, we have that the xy plane equals cosine theta sine theta, where theta is, grab a point there, theta is right here. This is the point cosine theta sine theta in the regular xy coordinate plane. But now if I'm modifying my way to the complex numbers, I have real part of z and the imaginary part of z, as now I have cosine, and actually this is really I times the imaginary part of z. I have cosine theta and I sine theta. Okay, so over here on the right-hand side, I'm going to modify this point to now be the point with an I sine theta. Okay, so that point there is cosine theta, comma I sine theta. If I want to think about I instead as a vector, right? I is the vector pointing in the up direction, and maybe 1 is the vector pointing in the direction to the right. Really, I can think about this as cosine theta plus I sine theta. And now I think this is making a lot of sense to everybody, because what is this number on the right? Cosine theta plus I sine theta. Back from Euler's identity, this is e to the I theta. So it turns out that the complex unit circle, is exactly the points z equals 1, the set, is the same as e to the I theta. Now, of course, theta doesn't have to be everywhere. Theta can stick from minus pi to positive pi. So this set e to the I theta, when theta moves from minus pi to positive pi, traces me around the complex unit circle. Okay, and I'll make sure to share a 3 blue 1 brown video that helps you out with that. But this is something very important. You know, if you take a complex analysis course, this is going to be kind of something you rely on the whole time. But let's, we just want to be aware of that because of where we're headed here. If I jump back to the book and I say I'm going to restrict myself here to the magnitude of z equals 1, then in fact z is actually e to the I theta for some theta in here. I should probably close the bracket, but we'll see why I leave it open later. So taking the point out that z is maybe not -1, we're going to keep the brackets open. But what we get is if we restrict my analytic functions who have a radius greater than 1, then they're defined on the complex unit circle. And I'm just going to study their behavior along the complex unit circle. So what I'm doing is I'm going to take this z and I'm going to replace that z with e to the I theta because I know that the function converges at e to the I theta. Okay, and in doing that, replacing z with e to the I theta, instead of investigating the domain of the function everywhere on the complex plane, or at the very least in some neighborhood of 0, I'm only investigating the behavior of the function as theta travels like this, right? This is theta traveling from minus pi to positive pi. I'm only looking at the behavior of the function around the unit circle. And this is in the domain, right? In the range, the function can be going up or down or left or right or something like that. And maybe I can represent that here by saying, okay, maybe the function goes up and then down, and it does something like this. Okay, so the function has some outputs, and of course these outputs are complex valued, but the function has its outputs in those directions, but truly it's complex outputs, not one-dimensional as it's drawn there. But really all I'm doing is I'm restricting the domain of the function there so that now the input and the output are only one-dimensional, right? So now the input and the output are just this theta, or the input is theta. F is now mapping minus pi to pi, and it's outputting a complex number. Okay, so that function is perfectly well defined, and it looks like the following. F of theta is now the sum of a sub n e to the I n theta, and that's perfectly valid for all theta in the range that I defined. But there's actually nothing special that said I had to define a clockwise rotation or a counterclockwise rotation. This is for a counterclockwise rotation. And it turns out I could totally define functions for a counterclockwise rotation instead. There's nothing special about a clockwise versus counterclockwise rotation, and to gain a counterclockwise rotation, I'm just going to plug e to the minus I theta, and of course that'll push me around the unit circle in the other direction. So I can find functions in my space of analytic functions which are now traveling in the counterclockwise direction as well. So I have these functions traveling in the clockwise direction, in the counterclockwise direction, and there's nothing telling me that I can't add those two functions together, right? I can add a function with a clockwise rotation to a function with a counterclockwise rotation, both coming out of these analytic functions, and what I recover is a series in the positive integers of e to the I n theta, and a series in the negative, this is the clockwise version, a series in the negative integers of e to the I n theta, right? What I've done here is I've called b star is really b of negative n, because what I'm doing is I'm translating my anti-clockwise rotation, I guess in that case, I'm translating my clockwise rotation into the negative integers, and so I'm just redefining b star as b of negative n from before. And this way I can keep all of my powers of e as, technically positive powers, even though I'm inputting negative numbers in there. So what I do is I have this new function h of theta that's really a superposition of the counterclockwise rotations of these analytic functions and the clockwise rotations of the analytic functions, and I superimpose them on each other. And what that is just a new function. If I give myself the ability to grab coefficients c sub n from these coefficients that I extracted before, I'm just going to define them in a very normal way. We have this collection of functions, the collection of functions h of theta, which is built from these coefficients that come from analytic functions with radius of convergence at least 1. It's built from these coefficients traveling from them in both a clockwise and anti-clockwise direction, and I can represent those by c sub n e to the I n theta. But n, to encounter both clockwise and anti-clockwise rotation, has to vary from all the way from minus infinity to plus infinity. This is basically what we're going to call the Fourier space. So I'm going to use a math cal or a calligraphic F sub the interval that I'm looking over my Fourier space at. And right now I'm going to say this is approximately defined the way that we introduced it so far. So it's approximately defined like these functions h, where I can build the c sub n's in the positive direction from analytic functions with radius at least 1, and in the negative direction from analytic functions with radius at least 1. So I'm going to grab these positive and negative coefficients out of this analytic function set, and I'm going to plug them into the negative and positive directions here, and then gain my functions of h. That's what we want to think of as the Fourier space for now. And we'll see that we can expand this idea just a tiny little bit. But now I want to introduce this lemma, because this lemma is very important for the construction of the Fourier series. It basically says, hey, suppose I'm going to perform an integral along this unit circle, right? Suppose my function, it has its little outputs that might just be whatever they are along that unit circle. Who knows what the function looks like along the unit circle. But if I integrate that function along the unit circle, and in particular, for some reason, if maybe the function had a very specific integral, where this is my version of trying to describe the complex exponential being the output of that function, then the integral of that function should either be 0 if the number of wraparounds is not the same as the input. We don't want to put too much effort into trying to visualize what this is. More importantly is just that the fact that if I take an exponential of some frequency and I multiply it by the reverse direction exponential of a different frequency, I have my k's and n's backwards there. If I multiply the clockwise rotation by an anti-clockwise rotation and I integrate as a line integral along that unit circle, then my output's either going to be 1, this needs to be normalized, it's either going to be 1 or it's going to be 0, depending on whether or not the frequencies were the same. And actually showing that that's true is going to be an exercise for you. But we're going to see why this is one of the nicest qualities that two functions can have. If I multiply them together and integrate over their domain, if they have this sort of property, it's very nice. So it turns out with this Fourier space, because of this property, because of this really nice property that I just made us kind of think about a little bit, if I take any two functions here, which I've defined from these analytic functions, and I take one of them on theta, and I take its conjugate, which just means I'm rotating in the other direction than I originally defined the first one. If I take one and then a conjugate of the other, and I integrate over their domains, and I normalize that integral, then I sum all of the coefficients. It turns out that the only pieces which survive that integration are exactly the coefficients because of this property here. So I can say that the integral of two of these functions, which I defined in this abstract space, which I'm going to call the Fourier space, the integral of two of them against each other is just the sum of their coefficients if you represent them by their, what we're going to call a Fourier series. That's known as Parseval's theorem. And actually I have a proof of that, right? So you can see the proof here. It's a little bit lengthy, but you'll see that it relies on the previous lemma. There's a version of this which is just called the Plancherel theorem, and that's where I'm taking the function h with itself rather than h1 and h2 from before. So if I take h along with itself, then of course I'm just going to recover the complex magnitudes of the coefficients from the series. Okay, so now I can actually define what I'm going to call the Fourier space, and which is going to play a huge role in our course the entire semester. So this space is, I'm going to broaden my abilities on the bounds, right? I started with minus pi to pi as my bounds on theta. If I broaden that, it's just a simple change of variables. But if I make the change of variables of minus pi to some theta 0 and the variable pi to theta 1, I would just extend the length of my interval or shrink my interval. Then it turns out that the coefficients, or rather the basis elements, have to modify. They have to modify so that instead of just being I and theta, they become 2 pi divided by theta 1 minus theta 0. And we can just verify really quick. Suppose theta 0 were minus pi and theta 1 were pi. Then up here, theta 1 is pi minus negative pi. I end up with 2 pi in the denominator. 2 pi over 2 pi is 1, and we recover exactly what we had before. So the Fourier space is really going to be this collection of functions whose basis elements are e to the in, and then this very special coefficient here, which depends on the length of the space I'm looking over, and that's defined within the space itself. And the coefficients have to satisfy one very particular property, and that's that it's clear that if I consider my analytic functions on the unit circle, those functions are finite, right? And so if I consider the magnitude of the analytic function over the unit circle here, no matter what my analytic function looked like along that unit circle, if I take the magnitude of that, it's some finite number. And if I'm integrating from minus pi to pi, that's also a finite number. So this infinite series of coefficients must be finite. And that's how I'm going to define the Fourier series. It's just going to be the collection of these sums of exponentials, right? I'm taking coefficients of exponentials with an imaginary power, and all I'm requiring is that the sum of those coefficients squared, their magnitude squared, happens to be finite. In math, we use this notation that strictly less than infinity is the same as finite. So we call strictly less than infinity means finite. Okay, so that's what we want to think about whenever we see the strictly less than infinity symbol. So as long as the coefficients squared in magnitude can sum to something finite, that's what we're going to call the Fourier space. Or possibly the Fourier series. The Fourier space is this entire space. The Fourier series is in particular the series which represents the functions in the Fourier space. Now it turns out we have a really nice property, or a nice way of extracting the coefficients c, supposing maybe we were given the function h by some other means, right? Suppose we were given h of theta equals sine of theta or something like that, and maybe we want to find the Fourier series. We can find the Fourier series using the following integral for c sub n, and that's called the Fourier series of h. So if we look at an example here, we can represent the identity function, h of theta equals theta. We can represent that as a Fourier series in the Fourier space, and every Fourier space must be paired with an interval, which is it's a space over. So I'm going to choose minus pi to pi here, and I can grab the identity function, and I can compute using the definition above. I can compute, letting theta 1 be pi and theta 0 be minus pi, the following integral for c sub n. If I compute that integral, it doesn't take me very long, one round of integration by parts, and I'm there, to see that c sub n is always going to be I times negative 1 to the nth power divided by n, so long as n is non-zero. And if n is 0, it makes a lot of sense. Theta is an odd function, and e to the 0 power is 1. I'm integrating something odd over symmetric balance, and I'm going to get 0. So the c sub n's take this very particular form, which means that I can represent, this is a representation of theta of the identity function h of theta equals theta as a Fourier series. Right, in this sense, if I jump back to kind of this idea of being on the unit interval, I'm asking myself the question, okay, given restricting myself to the unit interval, the identity function, it might not be clear that the identity function is a function which looks like this. It's kind of the function which starts down here, it comes up to the unit interval, and that's my origin on the unit interval, and then it kind of raises to the top of here. Okay, so that's kind of the identity function moving around the unit interval, and that's going to be equal to some, there's some analytic function which like agrees with the height of that function if I decided to plot it all the way around there. How do I find the coefficients for that analytic function? Well, it's exactly by these, right? So the analytic function, which is built like that, if I restrict it to the unit circle, looks like the identity function on that unit circle. So this is the Fourier series representation of the identity function. And if I decided to plot this, right, theta is purely real. It's purely real valued. And this and that are not real valued. So you wouldn't necessarily expect that the image, if I plotted some of these partial sums, that it's actually real value, but it is, and it turns out that will always be true. So let's look at some of the partial sums here, just plotted as real value functions. So I'm going to plot the partial sums. I'm going to call these theta sub capital N, and these are just the partial sums of that Fourier series. And I'm going to use their coefficients and the exponentials, and I'm going to let capital N be 1 in red, 10 in orange, and 100 in gray, as well as theta, the identity function itself. And now I'm just plotting these from x to y on the xy plane as any standard generic function would be plotted. And there we can see it. So what's going on here is that we have our identity function theta, right? That's that diagonal line that we like to always see with the identity function, like f of x equals x, for example. And in red, I'm going to let n equal 1. So I'm going to say, what is the Fourier series which approximates the identity function up to a frequency of 1 oscillation over the interval? And we see that this is the closest approximation we can get to 1 oscillation over the interval. And if I spread this, or I increase my frequencies to at least 10 oscillations over the interval, we see that we have 1, and then if we counted these oscillations, we would have 10 oscillations over my interval. And if we go up to 100 oscillations over the interval, then we can get closer and closer to the actual function. But there's something important that I want to note here, and that's that at the 10 and especially at 100, we start to see some really rapid oscillations, right? These little squiggly lines here are oscillating really rapidly right at the end of the interval. This line where it's crossing right here is right at minus pi, and that's at plus pi. So there's my interval from minus pi to plus pi. So we oscillate very rapidly near the boundaries. And more importantly, the function theta is not perfectly reconstructed. It's periodic, right? The function theta becomes periodic under the Fourier series. The Fourier series can only see this interval, the open interval, on pi. So if I restrict myself to the open interval right at pi, then everything would look perfect in the limit. You can see those oscillations, even though they happen very rapidly, they get very tiny. So they're rapid, but they're small near the boundary, which means in the limit it would perfectly approximate my original function, but it can only do that over the open interval, minus pi to pi. And then it forces periodicity over the interval, which means if I extend the domain to larger and smaller values, I get periodic behavior, right? I'm getting that the behavior of my series right here, it perfectly matches the behavior of my series right there. So that's something to keep in mind about Fourier series, is that you can put non-periodic functions into them, but the reconstruction is necessarily periodic. But why do we actually care about this series? These are great things, and we like the representations we have, but the most important part about the Fourier series, that's what makes it maybe the most important vector space of functions, is that this is a vector space with a well-defined inner product. But that is a story for the next time, so we'll end there and see you in class.